will create, if you take the modulus of the positive q charge is a q e. If you take the modulus of the negative q charge, here it will be negative q charge, it will be again qe. So here it will produce also qe. Here is also, it will produce also qe charge. This is the force in terms of the. If we want to figure out the net force experienced by the dipole, normally for dipole we consider everything, the distance, force experienced by the part from the center of the dipole. If you remember the center of the dipole part, we part. So if that is the case, that means from the center of the dipole, at the center of the dipole, what is the net force experienced due to this particular two force? It will be equal and opposite. That means it's a zero. So zero is the net force experienced by the center of the dipole due to these two particular force. They are trying to pull the dipole in two different directions. They are equal and opposite, so they cancel out each other. But so that means what? That means the center of the dipole will not move. Center of the dipole is the pivot point. It will not move. It will remain static at this particular space. But if you see the line of application of the force, with respect to this particular center of the dipole, if you see here the force is acting in this particular line, here the force is acting in this particular line. If you see, they are not aligned with the center. As a result, what will happen? It will experience a torque. That's the main idea, because the line of application of the two different force is not in the same line. As a result, it will experience a torque. So if you remember, let me go back to the whiteboard. Sorry. If you remember, so what is the line of application part here? So let's see, this is my dipole, this is positive charge, this is negative charge, this is my center of part. If my electric field is like one, in that case my force will be, F part will be like this, F minus will be like this. And if you see the line of application, they are in the same line. As a result, they will cancel out each other. Even they will not experience any kind of torque. But in this particular scenario, there is line of application is different. As a result, it will experience the torque. It will depends on the angle it creates with the external electric field. And if you remember the torque, how normally we consider torque, tau is a vector component. It's a, আমি নর্মাল জেনারেল টর্কে যাই, জেনারেল টর্ক রিপ্রেজেন্ট করি। টাও এ যদি আপনাদের মনে থেকে থাকে, আপনার ফিজিক্স 107 এ যেটা পড়েছিলেন, r cross f. R is the moment arm length, that means from the pivot point to the applied force direction, applied force position distance, and f is the force part. Okay, so this is the part here. If you remember, if you take the magnitude of the tau, it is rf sine theta. So theta is the angle it's creating. Okay, so now let's see in our case what is happening part. If you take a dipole, let us consider when we are taking what is r. Our problem is what is r. So r, you can start your journey from any particular. So let's see, this is my dipole, this is my negative charge, this is my positive charge, and this is my middle point. So this is my pivot point. I want to figure out the moment arm length for the negative force, moment arm length for the positive force. Okay, so for the first one, let's start. I start calculating from here. So this is my 0. From here to here, I said this particular distance is x. Let's see, I mentioned. So that means from the negative charge, the moment arm length is the x. So for the positive charge, what is the moment arm length? So if this is the center point, this is positive charge, so moment arm length is this side, r this is this side. So this is d minus x. This is the moment arm length for the positive charge from the pivot point. If this is x, this is d minus x. That is the two different direction of the r part. R is the vector component here, right? So same thing is happening here. So we are going to calculate the torque. So let's see the torque negative. Torque experienced by the negative charge due to the negative force. What is the part here? It will be, in terms of the part here, it will be x f minus sine theta. And for the tau positive charge, it will be d minus x f plus sin theta. That's it. Now
usually pivot পয়েন্টটা তো
pivot
ঠিক
point
মাঝখানেই
মাঝখানে,
হবে,
কারণ
right?
এটা হচ্ছে center of the dipole,
So
always
it's
center of the
just gonna be negative of the same thing.
নর্মালি আপনি ফোর্স ক্রিয়েট করছেন কোথায়, এটা যদি ধরেন, এটা যদি জিরো ধরেন, সাপোজ এটা জিরো, তাহলে হচ্ছে এদিকে হচ্ছে এক্স ধরলেন, তো এটা নেগেটিভ এক্স হচ্ছে। কিন্তু আমরা ওইভাবে করে ক্যালকুলেট করি, আমরা একটা এন থেকে ক্যালকুলেট শুরু, এটা জিরো ধরে, এটা এক্স, এটা হচ্ছে এক্স, তাহলে এদিকে হচ্ছে কত, ডি মাইনাস এক্স। ব্যাপার বুঝছেন? তাহলে এটার থেকে
Yes.
ডিস্টেন্স হচ্ছে ডি মাইনাস এক্স, এটাই হচ্ছে, কারণ ডিটা হচ্ছে আপনার ডাইপোল লেন্থ, টি মাইনাস এক্স এ আছে ওইটার পজিশনটা। তো দুটো সেন্টার আমরা জানি, কিন্তু ধরে নিলাম যে ইন কেস মিডল না, তাহলে হচ্ছে আপনি দুই সাইড থেকে এভাবে করে ধরে নিচ্ছেন, এই ক্যালকুলেশনের সুবিধার জন্য, জাস্ট ফর দ্য ক্যালকুলেশন পারপাস। আপনি টোটাল মোমেন্টামটা পরে দেখবেন এটা ক্যান্সেল আউট হয়ে আপনি ডি পাবেন, ঘুরে ফিরে শেষে ডি আসবে, আপনি ক্যালকুলেশন করে দেখেন। তো আপনি যখন এটা দেখেন, তো আপনি এটা হচ্ছে আমাদের জেনারেল পার্ট, এফ এফ ইকুয়ালস টু এফ প্লাস, বোথ আর সেম, কিউ, আমরা এটাও আগে দেখেছি। সুতরাং আমরা ঘুরে ফিরে সবকিছু একই পাবো। তাই এখন আমরা যদি সব বসাই, তো হোয়াট ইজ দ্য নেট টর্ক, net torque experienced by this particular due to this particular point, what will be the net torque? Net torque will be fx sin theta plus f d minus x sin theta. If you do simplified part, you will get f d sin theta. Now f is the what, the force, net sorry, force, d is the dipole length, and this is the simple tau part, the sine theta. Now, if you remember, f is what? If you take the modulus QE, and if you want to keep the d, fine, and if you want to place it in terms of the p, is the same thing. So if you want to calculate here again further, you can put f equals to QE and d equals to p by q. After simplification, you are getting PE sine theta. So the magnitude of the tau is, or torque is equals to PE sine theta. If you want to write it down into vector form, how it will look like in the vector form, if you remember the sign, that means it's a cross product. That means you can write it down in the vector form, P cross E, both is vector component. So you can write it down this particular way. If you take the modulus again, you will go back to the original shape. So this is the torque experienced by this particular part here. Now, if you notice this particular one, the sine theta, what is the value of the, uh, when the value of the sine is maximum, when is minimum? If you remember, when your dipole will be properly aligned, that means when the theta will be zero, that time the sine 0 degree is zero. That means your torque will be zero. When the your initial position of the torque will be 90 degree perpendicular with the electric field, it will experience the maximum torque, because it's a 90-degree shift. It has to turn 90 degree to align with this particular one. So that means sine 90 degree equals to 1. If you somehow align it anti-parallel, that means if you rotate it and make the positive charge here, negative charge align like that way, you see in this particular case, it will be again zero. So the torque will experience the zero torque. It is still stable. You can stay that one. We will talk about the other thing here. So it is like that one. So you see the range of the torque will vary from 0 to maximum, that means PE, to 0 again, depending on the how you orient it with the external electric field part. Okay, so let's come back to the whiteboard. So we saw tau net equals to PE sine theta. Now, when theta equals to 0 degree, then we are getting tau equals to 0. When theta is 90 degree, you are getting tau is max. That means you will feel the maximum orientation. That means the PE. When theta is 180 degree, that means tau equals to 0 again. Now, what the hell is difference? What is the difference part? I already mentioned, but let me show you drawing first. আমি দুইটা ড্রয়িং করছি, ধরেন এটা আমার ইলেকট্রিক ফিল্ড, এক্সটার্নাল ইলেকট্রিক ফিল্ড এদিকে কাজ করছে। Somehow original part is the very easy. That means if your dipole orient and stay like that one, then it's very simple. Your F positive is working this side, F negative is working this side, they align. Now theta, that means the P and E create 0 degree angle, so you are getting this particular scenario. 90 degree আপনারা বুঝছেন, 90 degree হবে এরকম, এরকম হবে, plus minus charge. So P is this direction, P. So it's a 90 degree. It will explain the maximum torque. But what if you do something like that? You somehow orient your dipole like that way. In that case, what is happening? The force will be like that. Negative. Get the idea here? In this particular scenario also, this is scenario is this one. If you see, now in both cases you are getting the torque equals to 0. Both case your system will remain in equilibrium position. If you remember the chapter equilibrium you learned into physics 107, is the same scenario. Both case you are getting the equilibrium. That means your, if you can place it like that one, it will remain stable. But this one, this one is a stable equilibrium, and this one is an unstable equilibrium. If you remember the stable equilibrium and unstable equilibrium, it's like a what? If you place a marble into a convex surface, it is a stable equilibrium. If you remember, that means if you even if you vibrate your this particular whole system, your marble will keep on oscillate, and eventually after some time it will come back to the original state. This is the stable equilibrium. And if you somehow balance your marble on the convex surface or concave surface, what will happen? With a little vibration, it will fall and it will never come back to the original state. Same thing is happening here and here. Both is stable, both is equilibrium, but one is a stable equilibrium. So even if you try to, if you apply the external force and try to rotate, it will come back to the original state. So this is a stable equilibrium. But for this one, with a little perturbation, with a little vibration, even for the little vibration, it will just flip and go back to and take the shape of this one. So and will never come back to the original state. So this is the unstable equilibrium. Now, how the system's stable and unstable equilibrium, how can you decide that one? Based on their potential energy. If you remember, if you can calculate the potential energy of the system. So when the object is in stable equilibrium, that time it has a lowest potential energy, always lowest energy. It try to always be in the lowest energy state. So this particular case, you have the lowest potential energy. Here you have the maximum potential energy. It's stable, but when it will get the chance, it will just flip violently without any reversal and go back to the lowest potential energy. So like this one, it will just fall and go to the stable potential energy state. This is what will happen. Okay. So now here you can see this orientation also link with the potential. So we will now learn about the potential energy of the dipole due to their orientation into the external energy. So potential energy of the electric dipole. So potential energy is a measure of the work required to assemble the dipole in the presence of external electric field. It is a scalar quantity, so it is denoted by the capital letter U, and it is a scalar quantity. It's an energy, so it has a unit of joule. The potential energy of an electric dipole in an external electric field depends on the orientation. Depending on the orientation, you can calculate that one. And mathematically, how can you place that one? U equals to minus P dot E. So it's a dot product of a P dot E. So dot product will give you the scalar quantity. So U is a scalar quantity. So this is what it is. U equals to minus P dot E or minus P E cos theta. So potential energy is calculated like that. Now, as you can see here, when your system is oriented with the external electric field, it has a lowest potential. How? When the theta equals to 0, then U will be equals to minus PE, because cos 0 degree equals to 1. When theta equals to 90 degree, that time U will be equals to 0, because cos 90 degree equals to 0. When theta is anti-parallel, 180 degree, then U will be equals to plus PE, because cos 180 degree equals to -1. So you can see in this particular orientation, your U will be max because plus PE, and in this orientation U is minimum because of minus PE. So that's why the dipole's preferred position is always try to orient with the external electric field, and in the process the direction of the electric field is from the negative to positive change. This is how the thing is working. So get the idea. In the lecture note I also showed you the proof of this particular one, so here I'm not going to spend time to show that one. It's just to prove that same equation one. We can prove it by external electric field. Okay, any question from this particular
স্যার
orientation part?
আনস্টেবল স্টেটে কি ওই ইলেকট্রিক ফিল্ডের ডাইরেকশনটা কি নেগেটিভ কি পজিটিভই থাকে?
হ্যাঁ, ইলেকট্রিক ফিল্ডের ডাইরেকশন একই। আনস্টেবল মানে কি, আপনি ইলেকট্রিক ফিল্ডের অপোজিট আপনি বসাইছেন, এমন ভাবে বসাইছেন যে দুটা ফোর্স স্টিল, এখন দেখেন এখানে দুটা ফোর্স কিন্তু স্টিল, আপনি দেখেন দুটা ফোর্স কিভাবে কাজ করে। কি ই তো এদিকে, ই এর সাপেক্ষে তো আপনি বলছেন আনস্টেবল। ই যদি আপনার উল্টা দিকে হয় তাহলে তো আনস্টেবল হলো না। ই এর সাপেক্ষে আপনার ওরিয়েন্টেশন আপনি এমন ভাবে বসাইছেন, এমন প্রিসাইসলি এটার উপর বসাইছেন, তার মানে আপনি একটা সুইকে আপনি আপনার টেবিলের উপর একটা ভার্টিক্যালি ব্যালেন্স করতে পারেন না? সার্কাসে করতেছে না? করতে পারেন, কিন্তু আপনার অনেক বেশি স্কিল লাগছে, অনেক বেশি ধৈর্য সহকারে আপনি বসালেন, কিন্তু এটা খুবই আনস্টেবল। একটুখানি বাতাস বা একটুখানি ভাইব্রেশন হওয়ার সাথে সাথে এটা ঘুরে যাবে। কিন্তু আপনি খুব প্রিসাইসলি আপনি বসাইছেন হচ্ছে আপনার ডাইপোলটা কিভাবে, এমন ভাবে বসাইছেন একেবারে ফ্ল্যাট, তার মানে হচ্ছে একেবারে 180 ডিগ্রি, কোনো ঝামেলা নাই। এই ফোর্সটা কাজ করছে এদিকে, এই ফোর্সটা কাজ করছে এদিকে, তার মানে দে আর ইন ব্যালেন্স, বাট স্টিল দেয়ার লাইন অফ অ্যাপ্লিকেশন, লাইন অফ ফোর্স ইজ এক্স্যাক্টলি ইকুয়াল এন্ড অপোজিট, দ্যাটস ওয়াই দে আর ইন ব্যালেন্স। বাট যখনই তারা সুযোগ পাবে সাথে সাথে ঘুরে যাচ্ছে, তার মানে হচ্ছে আপনার কোনো কারণে বসানোর সময় যদি কোনো কারণে এটা 179.9999 হয় তাহলেও সেটা ঘুরে যাবে, একেবারে 180 না হলে। বুঝছেন জিনিসটা, ঘটনাটা কোথায় হচ্ছে? কারণ হচ্ছে তখন তো এটা ব্যালেন্স নাই, একটুখানি সুযোগ পেয়েছে সে ফ্লিপ হবে, কারণ হচ্ছে সে আর ব্যালেন্সে থাকবে না। একেবারে 180 ডিগ্রি হলেই সে ওই আনস্টেবল ইকুইলিব্রিয়াম পজিশনে স্টেবল থাকবে, মানে কিন্তু কিছু ভাইব্রেশনের সাথে সাথে সে একটু করে ঘুরে যাবে, ঘুরে সে জিরো পজিশনে চলে যাবে, কারণ এটা হচ্ছে আনস্টেবল। তার জন্য কারণ ফোর্স তাকে চেষ্টা করতেছে এদিকে নেয়ার। এফ আর কিন্তু এখনো আছে, খালি এটা আর এর ডাইরেকশন এবং এফ এর ডাইরেকশন একেবারে অপোজিট হয়ে যাওয়ার কারণে সে ঘুরতে পারতেছে না, মানে একেবারে পয়েন্ট হেড অন কলিশন। কিন্তু একটু যদি সুযোগ পায় সে সাথে সাথে ফ্লিপ করবে। ব্যাপারটা বুঝছেন পার্থক্যটা কোথায়? আর আগেরটার ক্ষেত্রে দুইটা ফোর্স দুই দিকে টান দিচ্ছিল, সুতরাং ওর আর ঘোরার কোনো লক্ষণ নেই, একই দিকে। আর এর ডাইরেকশন আর এবং এফ এর ডাইরেকশন একই দিকে ছিল, এখানে আর এবং এফ এর ডাইরেকশন অপোজিট, বিকজ দেখেন আর এর আর পজিশন ভেক্টর এদিকে, এফ ভেক্টর এদিকে। এখানে দেখেন পজিশন ভেক্টর হচ্ছে এদিকে আর এফ ভেক্টর এদিকে, যার কারণে এটা হচ্ছে 180 ডিগ্রিতে কাজ করছে। ঘটনা বুঝছেন কোথায় হচ্ছে চেঞ্জটা?
জি স্যার।
সেটাই। তো এটা হচ্ছে স্টেবল ইকুইলিব্রিয়াম বাট আনস্টেবল, লিটল পারটারবেশনে এটা ফ্লিপ করবে, এটাই হচ্ছে ঘটনা। তো আমরা এখন দুটো পার্ট পড়লাম, আমরা এখন দেখি কিছু ইন্টারেস্টিং পার্টে আসি। তো আমরা দেখেন এটার একটু ডাইপোল ইন নেচার। এখন দেখেন আমরা এটা নিয়ে কিন্তু এর আগের ক্লাসে আমরা বলেছি, সো নেচারে আপনারা ইলেকট্রিক ডাইপোল পাবেন which is equals to water molecules. Water molecules is naturally occurred electric dipole. So if you see the arrangement of the hydrogen atom, they are not 180 degree. They create like this kind of shape, like a Mickey Mouse shape. We call it Mickey Mouse shape. Okay, so it is not like that one. If the oxygen here and if the hydrogen is like that one, is 180 degree, then it will not create any dipole because they will cancel out each other. The force will cancel out each other because of this odd orientation of the hydrogen atom with the oxygen. You see, they create an clear line of separation. You know the oxygen is more electronegative material. That means all oxygen try to bring the electron towards him more. So he will bring the hydrogen electron towards him as well. As a result, oxygen become negatively charged, and oxygen end, hydrogen end looks like the positively charged. So this one is creating the pure separation of a positive and negative charge. As a result, it act like a dipole. You see, it's like a dipole in nature. Now, if you keep on flip-flopping the direction of the electric field, the dipole will try to orient with the electric field, and in the process they will vibrate up and down. And this particular concept we use into our day-to-day life to for cooking, where in the microwave, we use the microwave frequency. So microwave, we see microwave is nothing but a sine wave. So it's just a positive terminal, negative terminal. You just keep on flipping each time, keep on flipping the direction. So in the process, what is happening? The water molecules in your food try to align with this particular orientation of the electric field. And what is the microwave frequency? Microwave frequency is 2.45 gigahertz. So that means per second it is vibrating, changing the direction of the water molecules 10 to the power 9 times per second. Such a high vibration created heat, and as a result your food heat up, or you used to cooking. So if inside your food there is no water molecules, that means there is no naturally occur dipole in your food, you cannot heat up your food. That's the main idea here. So this is the technology we are using into day-to-day life. Okay, so how the your microwave works, it just keep on flip-flopping the direction of your water molecules with the at very high rate with the change of a electric field direction, and in the process it heat up and cook your food. Any question up to this point? If not, then we can quickly go through some mathematics and complete this chapter officially. So this is the first checkpoint problem. Can you guys answer me this particular problem? Give me the answer. If you see here, we have four different orientation of the dipole with respect to the external electric field. External electric field is the center one, it's given, it's fixed. You see, it's from left to right. And you place the four different orientation. Here you can see the direction of the P is like that. Here, direction of the P is like that. Here, direction of the P is like that. And here, direction of the P is like that. This is the direction. So as a result, you see, they are creating an angle theta with this external electric field. One is in the positive direction, one is in the negative direction, theta. They are creating the theta orientation. Now the question is, you have to rank them based on the magnitude of the torque. Magnitude of the torque, that means the tau, this one, you have to rank them, and you have to rank with the with in terms of the U potential energy, not the magnitude but the U potential energy. So what is the answer you think? Yes, raise your hand. So ki bolte chan?
So 1 and 3 should be the highest potential, and
Okay,
the magnitude is the greatest.
potential, okay, potential বুঝলাম, কিন্তু torque wise
Same হওয়ার কথা, cause এটার 180 ডিগ্রি, প্রায় 180 ডিগ্রি
yes,
ঘোরা লাগবে।
same. Okay, আপনারা যারা কেউ অন্যরা কি বুঝেছেন? অ্যান্সার ফর দ্য এ, উনি অ্যান্সার দিয়েছেন এবং অ্যান্সারটা রাইট। আমি অ্যান্সারটা বলে দিচ্ছি। অ্যান্সার কি হয়েছে? এ এর অ্যান্সার হচ্ছে অল টাই, অ্যান্ড বি এর অ্যান্সার হচ্ছে u1 equals to u3 greater than u2 equals to u4. এটা হচ্ছে অ্যান্সার। নাও আপনারা জিজ্ঞেস করতে পারেন কিভাবে হলো। ওকে, আমরা সেটা এখন দেখেছি। যারা বুঝেননি তাদের জন্য বলছি, যারা বুঝেছেন তো মিলিয়ে নেন উত্তরটা, আর যারা বুঝেননি চলেন আমরা একটু করে দেখি কি হচ্ছে, ঘটনা কি ঘটছে। আমাদের সূত্র ফার্স্ট ওয়ান আমাদের টাও, we know tau equals to p sin theta. That's it. ওকে, এটা আমরা জানি। তো আমাদের এখন দেখি প্রথমটা আমরা 1 2 3 4 সবার জন্য বের করি। লেটস ক্যালকুলেট tau 1. Tau 1, if you calculate the angle like that way, what is getting? We are getting PE sin 180 minus theta. From here you are getting PE sin theta. If you calculate the tau 2, you will get PE sin theta directly. কোনো ঝামেলা নেই। Now come to the sin 3. What we are getting? What we are getting here?
স্যার মাইনাস থিটা,
Yes. এখানে দেখেন sin 180 প্লাস থিটা, কারণ হচ্ছে 180 হওয়ার পরে আরো যোগ হয়েছে 180 প্লাস থিটা। সো এখানে আমরা পাচ্ছি মাইনাস পিই সাইন থিটা, আর ফোর্থ ওয়ানে পাচ্ছি
এখানে মাইনাস থিটা,
সাইন লেটস সি মাইনাস থিটা অর 360 মাইনাস থিটা। আপনি যেভাবে করে করেন 360 মাইনাস থিটা করলে যা আসবে, সাইন থিটা মাইনাস দিলে হচ্ছে এটা মাইনাস থিটা। ফাইন, আমরা পেয়েছি। বাট আমাদের গোল কি? ম্যাগনিটিউড। ম্যাগনিটিউড মিন্স হোয়াট? You have to take the modulus. So if you take the modulus of all this one, you will find all of them are same, because modulus নিলে sin নেগেটিভটা চলে যাবে, তাই না? ঘটনা বুঝছেন কোথায়? So আপনি যদি modulus নেন তাহলে হচ্ছে you will end up having all sin theta. So here you are getting all type. Get it? Get the idea? What is going on? Once you take the modulus, magnitude, modulus of the tau যদি নেন আপনি পাবেন PE sin theta. So all type. Now if you consider from the second one the potential energy, what is the equation of the potential energy? Minus PE cos theta. আমাকে কিন্তু এখানে ম্যাগনিটিউড টেকনিক্যাল বলেন, আমাকে বলছে মডুলাস পটেনশিয়াল এনার্জি। পটেনশিয়াল এনার্জির ক্ষেত্রে একই ঘটনা ঘটবে, আপনি একটা একটা করে করেন। U1 হচ্ছে এটা, আপনি যদি এখানে করেন কি পাচ্ছেন? মাইনাস PE cos 180 মাইনাস থিটা। সুতরাং আপনি যদি ক্রস 180 মাইনাস থিটা হচ্ছে কত? মাইনাস কস থিটা। তো মাইনাসে মাইনাসে প্লাস হয়ে যাচ্ছে, প্লাস পিই কস থিটা পাচ্ছেন। U2 এটা ডাইরেক্ট পাবেন হচ্ছে মাইনাস পিই কস থিটা। U3 কি পাচ্ছেন? U3 তে কি পাচ্ছেন? মাইনাস পিই কস 180 প্লাস থিটা। তাহলে এটা যদি আপনি সলিউশন করেন এটাও পাবেন হচ্ছে প্লাস পিই cos theta। আর ফাইনালি U40 এখানে যদি আসেন আপনি পাচ্ছেন মাইনাস পিই cos মাইনাস থিটা। cos মাইনাস থিটা হচ্ছে cos থিটা, সুতরাং ওখান থেকে আপনি পাচ্ছেন পিই cos থিটা। সো আপনি যদি এখন দেখেন ইন টার্মস অফ এ র্যাঙ্কিং, U1 U3 is the highest, which is equals to plus PE. So U1 plus U2 they are equal, and greater than U2 and U4, which is minus P cos theta. Clear that one, everyone? How the result came? How you get the result? বুঝতে পেরেছেন নাকি এখনো ঝামেলা আছে? হ্যালো, আপনারা কি আছেন না কেটে গেছে লাইন? আচ্ছা, ঠিক আছে। Okay, then move to the next part. So this is the how to this kind of problem is solved. Now let's do this math and then we are done. We move to the next chapter. So this is a simple math. I already did this one. Just again quickly show you guys this one here. You have a dipole with the charge is given. So 2n charge, that means the Q equals to positive Q equals to negative Q equals to 2e. This is what we have. Then we have d 0.78 nanometer, that means 10 to the power minus 9 meter. You have electric field strength given, so 3.4 into 10 to the power 6 newton coulomb. Now what we know the torque. What we know, p e sine theta. This is what we know, p sine theta. So if we have all the components, now what we can do, so p e sine theta, or we can write down q d e sine theta. আমি আরো ঝামেলা কমাই দিলাম। সো p সমান সমান আমরা জানি কি p সমান সমান qd, তো সেখান থেকে হচ্ছে pd sin theta. সো এখন ফার্স্ট ওয়ান a, parallel. Parallel means what? Theta equals to 0 degree. So theta equals to 0 degree means your tau সমান সমান কত পাচ্ছেন? Sin 0 means 0. আপনি যদি c তে যান, anti parallel. Anti parallel means what?
180 degree.
180. তাহলে tau 0 because sin 180 equals to 0. And b তে যদি যান, b তে শুধুমাত্র আপনি পাচ্ছেন
90.
পারপেন্ডিকুলার 90 ডিগ্রি। তাহলে 90 ডিগ্রি যদি করেন তাহলে হচ্ছে sin 90 ডিগ্রি ইকুয়ালস টু কত? 1। তার মানে হচ্ছে টাউ সমান সমান কিউ ডি ই। তাহলে এখান থেকে কিউ ডি ই এর মানগুলো বসান, বসিয়ে যদি ক্যালকুলেট করেন আপনি উত্তর পাবেন -22 নিউটন মিটার। So that's the result of this particular one. 0, 8.5 into 10 to the power minus 22 and 0 again. So A, B, C are result. So this way there is some other example, some other questions you can solve them at home. So with that one, this chapter is completed fully. So we are going to start the new chapter. Any question before we move on? Do you have any question? No. Okay. Then I moved on to the next one. Okay. So there is some other examples you guys can do. And this is done. Discovered. Now let me open the new chapter. So can you guys see this screen? It's working? Okay.
Yes, sir.
So now the new chapter that we are going to start is called the Gauss law. Gauss law. In this particular chapter, we are going to do exactly the similar thing what we did in the previous chapter. In this particular chapter also, we are going to calculate the electric field strength or electric field produced by different types of charge object, point charge, the continuous charge, like that one. But in this particular chapter, rather than using this old concept, previously what we saw is the old concept. For example, previously when you try to figure out how to calculate the electric field for a, let us consider we want to calculate the electric field for a this continuous long line charge distribution. How we did so? To do so, let's see, we want to figure out the electric field at the point P. What we did, we just first take a element. Oh, there is an element. Then we try to figure out the perpendicular distance of this particular point P from the particular length. Then we try to figure out what is the distance of this particular point from that particular element. Then you try to figure out what is the electric field produced here. Then you try to figure out the what is the sine component, cos component, which is the cancelling part, like this. So many kind of calculation you did. You remember that one, right? You remember this
Yes,
kind
sir.
of thing. Sorry. So this is the theta part. So in this case, what is actually main part here? You have to do a lot of geometry, lot of thinking. Okay, where is the element? What is this part? There is any symmetrical component here or not? So here you can see we will have the symmetrical component somewhere here. So the sine component will cancel out. So we did so many like this one. So Gauss said, oh, I don't need this kind of so many calculation to calculate the electric field. I can do it shortcut. I can find the shortcut way to calculate the electric field using my technique. So this is the Gauss law is all about. So how to figure out the electric field of this kind of different shape charge object in simple way. So Gauss used the concept of the symmetry. Gauss used the concept of symmetry and he bring the new concept of the Gaussian surface. Whenever there is any object, he just think, okay, it is, I wrap the full charge object with my Gauss surface, and then with based on the symmetry, I will calculate the electric field of that particular object. So he bring the concept of the Gaussian surface and the concept of the symmetry to calculate the electric field of this particular object. And this particular, in this chapter, we will learn about this particular one. So first thing, as I said, he bring the concept of the Gauss surface. So we will learn about the Gauss surface, what is Gauss surface, and also today, because this chapter will be completed in three lectures. In three lectures, we will complete this chapter. So today we are going to first learn about the concept of the flux, electric flux. What is electric flux and what is Gauss surface? How they are related. In the next class, we will learn about the Gauss law, and the final class we will learn about the application of the Gauss law. Okay, this is how the thing will work. Okay, let's see what we are going to learn in this chapter. So he bring the concept of the Gauss surface, something like that kind of surface. If you have the charge particle, let's say this is my positive charge. Positive charge is enclosed by the Gauss surface, and now I'm going to calculate from this particular concept. So this is the concept of the Gauss surface he is bringing. So let's see this what. So today our main learning focus is the flux, electric flux. We will learn about the electric flux. In the process, we will learn about the Gauss surface and how the electric flux works. So let's see first what is the Gauss surface, the concept of the Gauss. A Gaussian surface is a closed surface in three-dimensional space, through which the flux of a vector field is calculated. So he always consider there is a charge particle, and you have an imaginary three-dimensional surface that will enclose that particular charge. And in the process, the electric field line will coming and will be calculated based on that particular Gauss surface. Now let's go back to the whiteboard. If you remember in the previous chapter what we learned, for the positive charge, if you have a positive charge, it is creating the electric field line that is going outwards, right? You learned about that one before. If you have a negative charge, electric field line is coming from the infinity and entering the part here. That's it. Now you think Gauss is saying, okay, now I can think of an imaginary Gauss surface. I have a Gauss surface that is covering, enclosing this particular charge here, like that. So now what is happening? Now if you see, let's say I cannot see inside the Gauss surface. This is completely, this particular one is completely hidden. It's a black box kind of thing. I cannot see. It's just I can see the surface. If I see the electric field line coming out of this surface, I already know inside there is a positive charge. Get the idea here? If this is also, you can think of a black box. If you can see that, oh, okay, all the electric field line is going into this particular Gauss surface, you already know inside there must be a negative charge. That's why electric field line is going in. And this is the concept the Gauss use. He bring the concept of the Gauss surface, and he just said, I don't know what the hell is inside. I do not care what is the hell is inside. By looking at the electric field line coming out or going in, I can already know whether there is positive charge or negative charge is enclosed by that particular Gauss surface. And we will come back to the another more interesting part of the Gauss surface later. But this is the main idea. It's a kind of black box. By observing the electric field line behavior, you already know what the Gauss surface is enclosing, what kind of charge is enclosed by the Gauss surface. That's the idea here. Okay. Now come back to this one here. You can see here for the first problem, for the first Gauss surface, here you can see there is some charge. What kind of charge? Positive Q charge. So like previous concept, when you have the larger amount of charge, you represent with the larger number of electric field line. Same thing is happening here. You see here you have a positive Q charge. As a result, you see you represent the 8 line to represent the electric field line. So if you have the 2 times of the positive charge, 2Q, then through the Gauss surface, double the amount of electric field line is coming out. So you can, by comparing these two picture, you already know the inside this Gauss surface, second Gauss surface, the electric charge is larger compared to the first one, because the electric field line is coming out of that particular Gauss surface is more higher. Get it? If you now go for the negative charge, but it has a half of the charge, you can see we are representing it with the 4 electric field line, and it's inward. So I already know electric field, it is enclosing negative charge, and it is weaker than the first one. Why? Because it is a half. It's a half than the first one, because the number of field line going in is half of the A. So I know. Clear? Okay. For the first two, let's see. On the Gauss surface, normally when you represent something on the Gauss surface, so you already know the dimension of the Gauss surface. So I already know this particular one. Here we are focusing on the spherical one, symmetrical spherical one. It can be any shape. Here is the spherical one. Let's see. We know the distance here, r is the radius. So that means on the Gauss surface, on this particular Gauss surface, anywhere on this particular Gauss surface, you can figure out the electric field on that particular Gauss surface. So on this particular Gauss surface, electric field on the Gauss surface, on will be K, Q is the charge, by R square is the distance. So if that is the concept, so for the first one here, what will be the electric field on this particular, anywhere on this particular Gauss surface, will be E equals to K, capital Q, by R square, if R is the radius here. For the second one, if you want to write down, K 2KQ, because Q here is the double, by R square. If you see this third one, let's see, this one also has the same radius R. So in this case, what will happen? Because we are taking actual key, what is this one? Actually, this one is originally is modulus of the cube, right? So in this particular case, we do not care about the part. It will be K Q by 2R square. So this is how on the Gauss surface, anywhere on the Gauss surface, you can calculate the electric field. So electric field is calculated on the Gauss surface. This is the concept of the Gauss. So you put the Gauss surface, if you know the radius of the Gauss surface, or if you know the distance of the Gauss surface, you can calculate the electric field on the Gauss surface. And once you calculate the electric field on the Gauss surface, it is true anywhere on that particular Gauss surface. If you measure it here, you measure it here, or you measure it here, it will be same. If you take, let's see, I don't, there is charge, there is a charge particle. I don't, let's see net charge here. And your Gauss surface shape is something like that. For some reason, I don't care. For some reason, your Gauss surface shape is something like that. Once you declare this is your Gauss surface, by default, you are saying on that particular surface, electric field will remain constant. So if you measure it here, or you measure it here, your E is remain the same constant. That's the beauty of the Gauss surface. Once you say this is the Gauss surface shape and this is the part, on the Gauss surface, your electric field remain constant. This is the part here. This is how it's measured. So if it is symmetric, it's easy. For example, here is spherical, you already know. If it is not, so maybe that means here the electric charge is oriented in a way that is, it is creating this kind of odd shape. It is possible, because it can enclose multiple charge at a time. It can enclose multiple charge. For example, it can enclose positive charge, it can enclose negative charge. So let's see, it is enclosing positive 2q, half q, half by q negative, or let's see positive 3q. It can use all the charge. And then you are saying this is my Gauss surface. So the way it's oriented, this is my Gauss surface. So that means when you will calculate, first you have to calculate the net q. Net q. So net q is that positive 2q, positive 3q, negative half q, q by 2. So whatever you are getting, it will be your net q. And due to the distribution, this is the shape. So but on the surface, whatever the electric field is constant for that particular Gauss surface. This concept is clear for you guys? Okay,
Yes, sir.
so on the Gauss surface, electric field remain constant, and electric field you can calculate using the same concept. If you know the radius part, if you know the distance, that's it. If you know the direction from the center, That's it. So this is the way you can calculate that one. Okay, now here you can see the fourth example. Here you can see there is a one single charge particle. It's a negative 2q. So negative 2q, here negative 2q charge enclosed by two different Gauss surface. You can see here two different symmetrical Gauss surface. This is the Gauss surface 1. This is the Gauss surface 2. So in this particular case, what is the electric field on the Gauss surface? In this particular scenario, it will depends which Gauss surface is closer, it will have a stronger electric field. For example, if you want to figure out the electric field at the point P1 or at the point P2, then what is the result? Let's see. For the first one, radius is R1. For the second one, radius is R2. So here, the electric field for the P1 at the P1 region will be what? Q, Q, then 2R1 square, and electric field experience on the second Gauss surface will be K, Q, 2R2 square. So because R2 is smaller than the R1, so electric field on the second Gauss surface will be stronger compared to the first Gauss surface. Get the idea here? What is going on? Same amount of charge enclosed by the multiple Gauss surface. That is also possible. But then you have to calculate the electric field with respect to the distance. But if you calculate the flux, it will be same. Flux will be same for both because flux is different. We will come back to the flux later on. Concept of the Gauss surface is clear for you guys? Okay.
Yes, sir.
Now move to the next concept, the flux, electric flux, how the electric flux is calculated. Now, when we are talking about the electric flux refers to the measure of the number of electric field line passing through a given area. So now, if I delete this one, now electric flux, when you calculate, let's see, this is my charge. It is creating the electric field line here. So you have an area, like this is window, and maybe other person have a large window. So it is a larger area. This is a smaller area. So electric field, same electric field is passing through, and it is passing through here. So maybe you can say no more electric field line passing through like this, electric field line passing through like this one, and then more electric field line passing through this section, more electric field line penetrate through this one, like that one. If that is the case, you can say, okay, in the first one, number of electric field line passing through is smaller. The second one, number of electric field line passing through is larger. But if you at the end calculate, electric field line also depends on the not only the electric field line, but also depends on the surface area. The second one has a larger surface area compared to the third one. So at the end, if you just keep on calculating, you will end up having the same calculation depending on. We will come back to this one later, but doesn't matter. It is more interesting to see from the closed surface point of view. For the large surface, it is not understandable more. So okay, let's see what is the flux here. So in by definition, flux should be flux should represent the electric field line pass through. That means it should pass through perpendicularly. What does it mean? Let's see, this is my area window. This is the electric field. Sorry, not this is the not this is not the electric field. Let's see, electric field is creating something like this kind of angle. Electric field like that one. If like that kind of angle, that means if you remember in the vector chapter you learned, it's a vector parts. In this case, you can split into two components, right? So from here, you can split into horizontal and vertical component. It's the EY and the EX. EX represent the cos component, so E cos theta, and here is represent the E sine theta. If it is creating the angle theta with the horizontal axis. If that is the case, so in this particular case, by definition, when you are saying the electric field line passing through, that means it has to pass through, penetrate completely. Only the X component of the electric field line is passing through in this particular case. The Y component is not passing through. It's just piercing through. It's just going along the surface. So it's not passing through. So in the calculation, the Y component of the electric field line will not be considered. Only the cos component. That means the horizontal component that pass through, penetrating through the surface completely, only that one will be considered into the field line calculation or a flux calculation part. Okay, so this is
স্যার
the
স্যার
yes,
স্যার ওয়াইটা কেন হবে না আবার একটু বলবেন?
ওয়াইটা হচ্ছে নট পাসিং থ্রু, ইটস পিয়ার্সিং থ্রু। দ্যাট মিনস আপনি যদি একটা ধরেন, আমি একটা ক্রস সেকশন ভিউ দিলাম, এই যে এটা ধরেন একটা পাহাড়, আপনি একটা এটা রে এটা পাস করে চলে গেল, তাহলে এটা হচ্ছে পাসিং থ্রু। আপনি যদি আসলেন, এসে এটা হচ্ছে পিয়ার্সিং থ্রু, তার মানে আপনি পাস করছেন না, আপনি একদম ফ্ল্যাট চলে গেলেন, এটা তো পাসিং থ্রু না, তাহলে এটা ক্যালকুলেট হবে না। ঘটনা বুঝছেন? যেহেতু আপনি যখন ভেক্টরে কনভার্ট করছেন, আপনি ভ্যালুসি ইসে কনভার্ট করছেন, তখন আপনার দুইটা কম্পোনেন্ট পার্ট হচ্ছে, একটা হচ্ছে পিয়ার্সিং থ্রু, একটাতে পাসিং থ্রু। এক্স কম্পোনেন্ট ইজ পাসিং থ্রু, দেখছেন, and y component is piercing. That means এটাকে ফ্ল্যাট করে সারফেস along the surface চলে যাচ্ছে, ও পাস করছে না। যেহেতু পেনিট্রেট করছে না, সুতরাং it will not be considered into the calculation. Only the one calculated. তো আপনার যদি ইলেকট্রিক ফিল্ড এটা হয় যে উইন্ডো আপনার, আর আপনার লাইটটা সরাসরি এসে পাস করে চলে গেল, তাহলে পুরোটাই কনসিডার, কারণ এখানে কোনো ভার্টিক্যাল কম্পোনেন্ট নাই, এখানে পুরোটাই হচ্ছে আপনার ex equals to e, তাহলে পুরোটাই গেল। আপনার যদি ইলেকট্রিক ফিল্ড এভাবে আসে, তাহলে আপনার শুধুমাত্র হরিজন্টাল কম্পোনেন্ট will pass through, vertical component will reflect or pierce through the surface. It will not be considered into the calculation. Clear?
জি স্যার।
Okay. Now see some properties of the flux. The flux is denoted by the Greek letter phi. Phi. Sometimes it is also represented by, for electric field, electric flux, it's also give you the subscript phi e, because we also have the magnetic flux. So if you want to distinguish electric flux and magnetic flux, sometimes we write it also phi e, phi subscript e, and magnetic flux we write it down phi b. But here we are talking about the, when we, if you know that you are talking about the one particular flux, you can also present it with a phi, not divided. Unit wise is Newton meter square per coulomb. Newton meter square per coulomb is the unit. Flux is a scalar quantity. A scalar is a scalar quantity. So that means it does not have any direction, only the magnitude. Now, electric flux is a constant on the Gauss surface. On one particular Gauss surface, the way electric field is constant, same way electric flux is constant on the Gauss surface. If you take a charge and if you enclose a Gauss surface, it is creating an electric field line. So you can see electric field line also penetrating perpendicularly with the part here. And if you know the area of this particular Gauss surface, you can say on anywhere on this particular Gauss surface, flux remain constant. Flux remain constant on the Gauss surface. It does not depends on the radius of the surface. It does not depends on the radius. If it is a small, it is large, so it has the same flux. They have the different electric field. You remember, they have the different electric field, but they have the same flux. So what does it mean? I told you. So this is my positive charge. Let's see, I'm talking about the positive charge. I have a Gauss surface 1 and I have a Gauss surface 2. I have a Gauss surface 3. Now, this particular charge is creating the electric field. It's a E, electric field line, right? Electric field line. Now, previous we saw here electric field is E1. Here electric field is E2. They are different. They are larger. Here electric field is E3. So E1 is larger compared to E2 compared to E3. Why? Because E1 is smaller, is close to the charge. So সূত্রটা কি ছিল? KQ by R square. যেহেতু E1 এর R radius ছোট, ইলেকট্রিক ফিল্ড কিন্তু E1 এরটা বড়। আপনাদের এটা মনে আছে তো? হ্যাঁ? ক্লিয়ার আছেন এটা? এটা ক্লিয়ার তো কনসেপ্ট? কিন্তু আপনারা যদি এখন ফাই ক্যালকুলেট করেন, ফাই, সো এটার ক্ষেত্রে জানেন এই সারফেসের ক্ষেত্রে আপনার হচ্ছে ফাই 1, এটার ক্ষেত্রে হচ্ছে ফাই 2, আর এটার ক্ষেত্রে হচ্ছে ফাই 3। এই ক্ষেত্রে the both are equal. Phi 1 equals to phi 2 equals to phi3. Both are all are same. Why? Because what it says, it only depends on the charge it's enclosed, not on the radius. So it does not matter the radius. আমরা সূত্র মাধ্যমে পরে দেখব, সূত্রের মাধ্যমে আমরা পরে দেখব কেন এটা হচ্ছে কাজ। তো ফ্লাক্স ওয়াইজ আপনারা যদি একই ডিফারেন্ট গাউস সারফেস যদি সেম অ্যামাউন্ট অফ চার্জকে এনক্লোজ করে, if the same amount of charge is enclosed by the different gauss surface, they will experience the same flux, but they have a different electric field on the surface due to their shape size. That is the difference part. আমরা কেন তাই আচ্ছা এটা গেল এটা। Only the enclosed charge matter. Only the enclosed charge matter for the calculation of the flux, not the shape or the size. That's the main idea of the part.
স্যার, সো অনলি ইন্টেন্সিটি ম্যাটার করবে, যে ফ্লাক্স ইন্টেন্সিটি কেমন, এটাই।
ফ্লাক্স ইন্টেন্সিটি, ফ্লাক্সটা হচ্ছে শুধুমাত্র নির্ভর করবে যে কি চার্জকে, কোন চার্জকে এনক্লোজ করছেন। এটা কি যদি 1 কিউ চার্জকে এনক্লোজ করেন, আপনি যত বড় গাউস সারফেসই নেন না কেন, এটা যদি 1 কিউ হয়, তাহলে 1 কিউ যেহেতু এই সারফেসটা 1 কিউ চার্জকে এনক্লোজ করতে, এটাও 1 কিউ চার্জকে, এটাও 1 কিউ চার্জকে, the flux on the surface will be same because it depends on the charge enclosed by the Gauss surface, not the shape or size of the Gauss surface. বুঝছেন জিনিসটা? কিন্তু ইলেকট্রিক ফিল্ড ডিপেন্ডস অন দ্য শেপ এন্ড সাইজ। ইলেকট্রিক ফিল্ড, বিকজ ইলেকট্রিক ফিল্ড ছোট বড়র সাথে আপনার আর এর ভ্যালু ছোট বড় হচ্ছে। বুঝছেন জিনিসটা? এখানে ইলেকট্রিক ফিল্ডের ক্ষেত্রে আর আছে, কিন্তু ফ্লাক্সের ক্ষেত্রে আর নাই। এটাই হচ্ছে মেইন জিনিসটা। আমরা এটা পরে আবার আসবো। এটা হচ্ছে আপনার প্রপার্টি। দিস ইজ দ্য প্রপার্টি অফ দ্য ইলেকট্রিক ফ্লাক্স। নাও মুভ টু দ্য few characteristics, behavior of the electric flux and the electric field line. আমরা দেখি কিছু প্যারামিটার। Then আমরা কি জানি, as we know the electric field line originated from the positive charge and terminated in the negative charge. So from that particular point of view, if the Gaussian surface enclose a positive charge, then your flux is positive and it is known as a positive flux. If the Gaussian surface enclose a negative charge, your flux is considered negative and it is known as a negative flux. That is by definition. So if you know what kind of charge is enclosed by the Gauss surface, you know what kind of flux it will create, positive flux or negative flux. So that means electric field line coming out of the Gauss surface, it is considered as a positive. Electric field line going into the Gauss surface is known as a negative. That is the basic idea. If multiple charge is enclosed by the Gauss surface, then you have to calculate the net charge. That means what is the total charge after cancelling out positive and negative? If your net charge is positive, then it will create a positive flux. If your net charge is negative, it will create a negative flux. Rather than individual charge, then you have to consider the total as a whole charge. Now, what if whatever the electric field line generated outside by the charge outside the Gauss surface? For example, here you have a Gauss surface. It is creating some kind of electric field line like that one. Okay. So I already know this is positive. It is enclosing positive charge. How? Because this electric field line is coming out. Okay. Now let's see, there is another positive charge which is outside the Gauss surface. So it will not be considered into calculation. But it is also creating the electric field line, right? So what will happen to this electric field line? What will happen? So you will see this electric field line is going into the Gauss surface and it will bend and coming out like that. So for the external charges that is outside the Gauss, so for example, here is the, let's see, in this side there is a negative one. So you will see from the infinity, from outside, maybe electric field line come here, it bend and it just goes here. Something like that. This kind of thing you will observe. Electric field line is creating like that one. So you will see something like this kind of thing is continuously going on. So electric field line from the external charge that is outside the Gauss, it is not considered into the calculation. But in this case, what you will see, the electric field line, those electric field line coming in through some part of the Gauss surface and going out through another part of the Gauss surface. So as a result, they will not be considered into the main final calculation. So they are just cancel out. So at the end, we will only calculate the total number of electric field line into. So basic idea is that when the electric field line is coming out, you will consider as a positive one, plus one. When electric field line is going in, you will consider as a minus one. So for example, in this particular scenario, what I can say here, plus one, plus one, plus one, plus one. This one also creating plus one. Here I can see it's going out here, it's a plus one. But here you can see it is going in, so it's a negative one. Here it is going in, it's a negative one. So if you consider at the end, you will get plus 4. That means that plus 4 is originally creating by the internal charge enclosed by the Gauss surface. Other one that is coming in and going out, they will cancel out each other, because electric field line going in is plus 1, electric field line is going out is, sorry, electric field line going out is plus 1, electric field line going in is negative 1. So every time you just mark them like that one, and they will cancel out, and as a result you will get the original one. You see, original it is creating the 4 electric field line by the charge enclosed, so it remained the 4. Although I calculate 8 times, you can see 8 electric field line, but at the end you are getting 4 by after calculation. This is how the thing works. This concept is clear for you guys?
Sir, one question.
ইলেকট্রিক
Yes.
এক্সটার্নাল
Sir,
ফিল্ড
if
লাইনগুলো ব্যান্ড হচ্ছে কেন?
yes, sir, the negative, like the opposite charges should be attracted. So
না,
why
এখানে তো
does it bend?
অ্যাট্রাক্টের কথা না, এখানে তো আমরা ফ্লাক্স ক্যালকুলেশন করছি, এখানে তো অ্যাট্রাক্টের ব্যাপার না। আমরা এটা তো আসছে কোথা থেকে? ইনফিনিটি থেকে, মনে আছে? ইনফিনিটি থেকে আসছে, তো ইনফিনিটি থেকে আসছে, তো আমরা ইনফিনিটি থেকে পজিটিভ চার্জের ডাইমেনশন ইয়েটা আসছে, চার্জের ইলেকট্রিক ফিল্ড লাইন, তো এটা তো এসে ব্যান্ড হবে। এটা এখানে তো ঢুকবে না, কারণ এখানে তো পজিটিভ চার্জ রিপেল ইচ আদার। এটা বেন্ড হয়ে তারপরে বেন্ড হয়ে ইনফিনিটিতে ইসে ঢুকছে, এভাবে ঢুকছে। এখানে তো আমরা ফোর্স ক্যালকুলেট করছি না, এখানে আমরা দেখছি ফ্লাক্স ক্যালকুলেশন, মানে ইলেকট্রিক ফিল্ড লাইনটা কিভাবে বিহেভ করছে সেটা আমরা দেখছি। অ্যাট দ্য এন্ড হোয়াট ইজ দ্য ইলেকট্রিক ফিল্ড লাইন বিহেভিয়ার। আপনারা যখন লেকচার নোটটা পড়বেন আরো ভালো করে বুঝবেন ব্যাপারটা, বুঝছেন? এটা আরো তখন ক্লিয়ার হবে।
স্যার নেগেটিভ চার্জ আসলেও কি ব্যান্ড হবে?
হ্যাঁ,
নেগেটিভ চার্জ,
নেগেটিভ তো আর ইলেকট্রিক ফিল্ড লাইন তো গোয়িং ইনওয়ার্ডস, এখানে তো ইনওয়ার্ডের কিছু নাই, এখানে হচ্ছে সব ইনফিনিটি থেকে আসছে। আমরা তো ইন্ডিভিজুয়াল চার্ট চিন্তা করছি, আমরা তো কোনো পেয়ার হিসেবে চিন্তা করছি, আমরা ইন্ডিভিজুয়ালি চিন্তা করছি। কিছু তো যে কলাপস করবে সেটা আলাদা কথা, আমরা সেটা নিয়ে ক্যালকুলেশন করছি না। আমরা ক্যালকুলেশন করছি এটা হয়তো যে এখানে বেন্ড করে এখানে ঢুকবে, সেটা তো আমাদের ক্যালকুলেশনই না। আমাদের ক্যালকুলেশন হচ্ছে ইলেকট্রিক ফিল্ড লাইন কামিং আউট এন্ড গোয়িং ইন, দ্যাটস দ্য ক্যালকুলেশন। আমরা সেটা সিম্পলিফাইড ওয়েতে দেখাচ্ছি। এখন যদি বেন্ডিং দেখানো হয় তাহলে তো আপনাদের মাথা খারাপ হয়ে যাবে, ব্যাপার বুঝেন নাই? আমাদের কথা হচ্ছে গাউস সারফেস থেকে ইলেকট্রিক ফিল্ড লাইন গোয়িং ইন অর কামিং আউট, দ্যাটস দ্য মেইন আইডিয়া। এখানে কোনো ফোর্স টু স্কেল, ইন্ডিভিজুয়াল চার্জ সবগুলো ইন্ডিভিজুয়াল। সেক্ষেত্রে কি হচ্ছে, ধরেন এটাও পজিটিভ, আপনার ঝামেলার বাদ দেওয়ার জন্য এটাও আমি পজিটিভ করে দিলাম, তখন কি হবে? ইলেকট্রিক ফিল্ড লাইন তো আর এখানে তো রিপালসিভের কোনো ফ্যাক্টরি না, এখানে হচ্ছে আপনার কামিং ইন গোয়িং আউট। আপনি দেখবেন এরপরে আরো কি হয়ে যাবে, কমপ্লিকেটেড হয়ে যাবে ড্রয়িংগুলো। ঠিক আছে, এটা হচ্ছে মেইন আইডিয়া। আপনি খালি ক্যালকুলেট করবেন ঢুকলো বের হলো কয়টা, যেটা ঢুকবে সেটা পজিটিভ, সরি যেটা বের হবে সেটা পজিটিভ, যেটা ঢুকবে সেটা নেগেটিভ। আপনি অ্যাট দ্য এন্ড পজিটিভ নেগেটিভ ক্যালকুলেশন করে আপনি বলবেন যে আপনার ফাইনালটা কত, ওটাই নেটটাকে রিপ্রেজেন্ট করবে, সেটা হচ্ছে আইডিয়া। ওকে, এখন আমরা ম্যাথমেটিক্যালি দেখি কি আসছে। ম্যাথমেটিক্যাল আমরা একটু এসে যাই ম্যাথমেটিক্যাল পার্টে। ম্যাথমেটিক্যাল, আচ্ছা আরেকটা ছিল। এখন ইফ 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 the net charge within the closed surface is zero, net charge within the closed surface is zero, in this particular case what is happening? In this particular case, the field line directed into the surface will continue through the interior and is directed outwards. So যেটা বাইরে থেকে এক্সটার্নাল গুলো একদিক থেকে ঢুকবে আরেক দিক দিয়ে বাইরে হয়ে যাবে, সুতরাং নেট ক্যালকুলেশন এটা কখনো কনসিডার হবে না। আপনি যখন নেট ক্যালকুলেট করবেন তার মানে হচ্ছে যদি একটা গাউস সারফেস, ধরেন net charge enclosed by this particular Gauss surface is zero, so theoretically it will not produce any electric field line because there is no net charge inside, but externally there is more charges, external charges are there. So what is happening to them? This particular external one, electric field line coming in going out, they cancel out each other, going in here, going in, coming out. So this is what is happening. So আপনি এখানে যদি নেট ক্যালকুলেশন করেন, এখানে হচ্ছে নেগেটিভ 1 পজিটিভ 1 নেগেটিভ 1 পজিটিভ 1, আপনি এখন নেট ক্যালকুলেশন করেন চার্জ আর ফ্লাক্স নেট, you will end up having zero because you see if you add them up is zero. This is what is actually happening. For the zero part, it's more easily visible. Like actually, it's easy to draw the visual part. So the Gauss surface itself is creating zero electric field, but from external charges, electric field lines keep on penetrating, but they will cancel out each other. This is what is happening here. So for the net charge. Okay, now let's go to the drawing part. This is already I draw before. So mathematically, how can we say? You see, this is your full area. You take a small window, and on this window, your electric field line is like that one. So as a result, you can convert into vector component. As I said, the only the horizontal component is penetrating through the surface, so it will be considered into the flux calculation. This is piercing through or just touching the surface and going along, so it will not be considered into the flux calculation part. So according to the flux calculation, what is the mathematical part? So through this particular small window, the flux, so it's a small contribution of the flux, is the Ex, that means horizontal component, multiplied by the this particular area element. This is the area element of the this particular element part. Area element, a small area. The full area is a area element. So you can write down this is the cost component, E cos theta. So you can write down E cos theta. What is the angle here? The from the horizontal part, this is the theta. E cos theta A, you can write down EA dot. So it's a dot product formation. You can write it down in the dot product formation or this particular way. Now you can see we represent this particular vector area into vector form. This particular component new quantity, it is known as a area vector. This is the new quantity called area vector. Now, if you want to calculate the total flux, net flux through the full surface, then what? You have to do the integration. You have to find the total flux, you have to do the integration. What integration? The surface integration. Surface integration for this particular E dot dA, which is the vector. So electric field dot the area vector component. Now the question can be asked, what the hell is area vector? So now we have to learn about the area vector part here. Okay. Now you can see this particular equation is for what? Open surface. This is not the Gauss surface. This is open surface. Our Gauss surface is a closed surface, if you remember. This is for the open surface. This particular equation is for the open surface one. For us, we have to modify this equation. Okay, first, before modification of the equation, let's go to the area vector. What is area vector? Area vector, also known as the differential area vector or the area normal, is the vector that represents the direction and the magnitude of the area of the infinitesimal surface element. Okay. Area vector is a perpendicular on the surface. Area vector direction is perpendicular on the surface, and area vector magnitude is the area calculate. You calculate the area that will represent the magnitude, and direction is perpendicular on the surface. Now you can ask the question, perpendicular, but which direction? So let's see example. Let us consider a flat surface like a paper. If you take a paper, it has a two surface, up and bottom. Let's see you place it horizontally. Or you can think of your table as currently you are sitting on. So table has a two surface, up and bottom. Which perpendicular? If you take the perpendicular, it can be both upward direction or downward direction, doesn't matter. But for one particular problem solution, if you said upward is my vector direction, then you have to maintain the same vector. In the same problem, you cannot say in one case is upward, another case is downward. For the same vector, you have to maintain, for same problem, you have to maintain the one particular direction. Whatever you choose, up or down, it's up to you. But once you choose it, it's with you for that particular problem. But we are talking about the Gauss surface, and we said Gauss surface is a closed surface. Then what is the direction for the closed surface? For the closed surface is always perpendicular on the surface, and it's always pointing outward direction. Okay, so for the closed surface, you have to take a small patch element. You can see the element part here is mentioned. Here is the element. Here is the element. Whichever direction is the element, you have to draw the perpendicular on that particular element direction, and it will always pointing outwards, always outward direction. So by default, this particular Gauss surface by default is designed for the positive charge, because if you can think of a positive charge enclosed by the Gauss surface, it will create a electric field line coming out, so that means it will be parallel to the area vector. If you think of a, no, it's my thing is a what, my area vector is sorry, my charge is negative charge, then what will happen? If your charge is negative, then by default it will be anti-parallel. If your enclosed charge inside the Gauss surface is negative, that means it will create an anti-parallel charge. So 180 degree. So this is the only two possible way the electric field line and the Gauss surface have, the Gauss surface area vector has, either parallel or anti-parallel. When the positive charge, it will be parallel. For the negative charge, it will be anti-parallel. That will be the original basic part. This is how the Gauss simplify the problem. Now I have one question for you guys. I didn't ask you this one. Do you guys know the difference between the closed surface and open surface? Do you remember? Can you give me an example of the closed surface and open surface?
So closed surface is which I can't determine the size of, suppose, a sphere.
Okay. Just simplify. If I simplify any surface, for example, you can think of a paper. Paper has the two surfaces, right? This side and this side. But both these you can touch. You can go from one surface to another surface by touching. You can easily. You can touch. You have the access to both surfaces. This kind of surface is known as a open surface, where you can have access to both the surface. You can touch both surfaces. But you can think of as football. You can think of a soap bubble. You can think of any closed surface where you do not have access to the internal surface. This is known as a closed surface. So soap bubble is a very good example of the closed surface. You can see soap bubble can, when you can create a large soap bubble, it can has a random shape. It has a random shape, but you cannot access the internal space of the soap bubble. So that is the internal. So it is enclosing certain volume. Closed surface always enclose certain volume, and you do not have access to the internal surface. This is called the closed surface. If you make a hole, like let's say you have a full football, so that means it is closing some kind of volume internally, and you do not have access to the that particular internal surface. So it is a closed surface. Now for some reason you cut your football, then suddenly you have access to the internal surface. Then it's no longer a closed surface, it become open surface, because you have it, you can continue your journey to the other surface. Get the idea here? Closed surface and open surface. So closed surface always encloses a certain volume, and you do not have access to the internal surface. That's it. Okay, so now let's modify our equation for the vector. So let's calculate the net flux. What is the net flux? Oh, okay. This is some example of the different shape of the closed surface we are going to talk in this particular chapter. So you can have a cubic shape. So if you have a cubic shape, you have a 6 different surface. So that means you have a 6 different normal on the part. So this particular surface has a area vector in this particular direction. This particular surface area vector is this particular direction. This surface area vector in this particular direction, and so on. Similar way, this one is here, this one is here, area vector here, like that one, so on. On the spherical part, you can take any element and you have a different direction part. You can see here, like that one. On the torus also, these are the different examples of the Gaussian surface that we are going to discuss in this particular chapter. So time to time. This is just example. Now focus on the last topics of today is the net flux. So net flux refers to the total amount of electric field line passing through a closed surface. Total amount of electric field line passing through a closed surface, and is determined solely by the charge enclosed by this particular one. By charge enclosed by this particular. That means you have a multiple charge enclosed by the Gauss surface, you consider the total net charge, and from there, if the net charge is positive, you will see the electric field line coming out of the Gauss surface. If the net charge is negative, you will see the electric field line going into the Gauss surface. If the net charge is zero, you will see nothing is coming out or going into the particular Gauss surface. Or if from some electric field line coming out from the external charge, it will come in and go out. So it will not be considered into the calculation. So it still remain, the net will remain zero. That is the main idea. Now, what is the then equation, modified equation for the closed surface? This is the modified equation. So your symbol change, you can see we are using the symbol for the closed surface integral. So only the change is the closed surface integral symbol. This one represent the, you are taking the integration on the closed surface. That's it, closed surface. So that's the expression part. So theoretical part done. আমরা এখন একটা ছোট্ট একটা ইয়ে দেখবো, কি বলে, একটা চেক পয়েন্ট দেখে আমরা আজকের মতো লেকচার শেষ করে দেবো। একটা অঙ্ক আমরা পরে করব, আর পরে আমরা গাউস সারফেস শুরু করবো নেক্সট ক্লাস থেকে। ওকে, সো আমরা এটা করি, এটা করলে আপনারা একটু বুঝতে পারবেন যে আমরা কি নিয়ে কথা বলছি এতক্ষণ ধরে। এই যে প্রবলেম, দিস ইজ দ্য প্রবলেম, এন্ড উইথ দ্যাট ওয়ান উই আর ডান টুডে। So it's a checkpoint problem. This kind of problem you have to solve just by looking at them. So you can do it, do the rough, but you do not have to, you do not show the mathematical, you do not need to show the mathematical proof. You just give the answer. You can do the calculation other way around. That's the thing. Here you can see the figure here. So we are talking about the cubic shape Gaussian surface, cubic shape Gauss surface. Okay, so shows Gaussian cube of face A. So এখানে A টা দেখা যাচ্ছে আমাদের দিকে ফেস করে আছে, is pointing towards the positive z axis. And if you see the electric field is given, is parallel to the z axis and it's working towards the positive z axis. This is what information is given. Now what you have to calculate in terms of the E and A, what is the flux, what is the flux of the front face? That means front face means this is front. Then what is the rear face? That means this back side, which is we cannot see, back side. That is the rear. Top, this is top, and whole cube, all the 6 face. You have to figure out this particular, the flux, the phi. So what is the answer? Can you guess? আচ্ছা, আমরা আসি এখানে, আসি দেখুন phi equals to flux আসছে কোত্থেকে, E dot A। আমি এখন DA না দিয়ে E dot A দিচ্ছি, ডট প্রোডাক্ট। তার মানে হচ্ছে কি হচ্ছে EA cos থিটা। এটা হচ্ছে আমার সলিউশন করতে হবে। ওকে, ক্লিয়ার? আপনারা আছেন না নেই হয়ে গেছেন? EA cos থিটা আমাদের সলিউশন করতে হবে এখানে। এখন আসেন এখানে, what is E direction? This for the front face, what is the direction of the A, DA? Also perpendicular on this surface, this one. So they are parallel. So that means angle will be 0 degree for the front face. So that means for this one, front face, what will happen? It's a EA cos 0 degree or EA. Get the idea?
Yes, sir.
Okay, now rear face. What is the rear face part? That one I cannot see. So rear face will be
EA
that direction.
cos 180.
180. So that means for the rear it will be EA
Negative EA.
cos, yes, this one. So minus EA. For the top, DA is this side. এগুলা কিন্তু D এর,
0 আসবে, right?
এগুলা কিন্তু D এর। Yes, 0, 90 degree. So that means for the top it will be 0. Why? Cos 90 degree equals to 0. এখানে থিটা হচ্ছে 90 ডিগ্রি। গেট দ্য আইডিয়া? আমরা তিনটা বের করে ফেলেছি, এখন আমাদের হোলটা বের করার জন্য কি হচ্ছে, আরো তিনটা বের করতে হবে, আরো তিনটা। এটার জন্য তাহলে আরো কি কি বের করতে হবে, লেফট রাইট অ্যান্ড বটম। বটম উইল বি এদিকে, দেখেন বটমেরটা এদিকে, রাইটেরটা এদিকে, আর হচ্ছে লেফটেরটা এদিকে। এখন আপনারা যদি খেয়াল করে দেখেন এই প্রত্যেকটা ক্ষেত্রে ই এর সাথে অ্যাঙ্গেল কত,
90 ডিগ্রি।
90 ডিগ্রি। সো আমি যদি বাকি তিনটারও বের করি, সরি, ফ্লাক্স বটম equals to flux right GHT and flux left,
So technically 0.
সবগুলো জিরো। সুতরাং আপনি যদি এখন টোটাল করেন, নেট করেন, তাহলে কি হচ্ছে 6টা ফেজেরটা যোগ দিবেন, তাহলে হচ্ছে প্রথমে হচ্ছে ইএ মাইনাস ইএ প্লাস 0 প্লাস 0 প্লাস 0 প্লাস 0, 6টা ফেজের জন্য 6টা। সো টোটাল নেট ফ্লাক্স ইকুয়ালস টু 0। সো আপনার হোল কিউবের অ্যান্সার হচ্ছে 0। কারণ কি দেখেন, এই ইলেকট্রিক ফিল্ড তো বাইরে থেকে পেনিট্রেট হয়ে আসছে, ইলেকট্রিক ফিল্ড কিন্তু কন্টিনিউ হচ্ছে কোথা থেকে, ওই দিক থেকে। তাহলে দেখছেন এটা কিন্তু ঢুকেছে বক্সের ভিতর আর এদিক থেকে বের হয়েছে। তার মানে কি হচ্ছে, the electric field line coming in, electric field line going out, that is generated by the external charge. Internally there is no charge, no net charge enclosed by this particular Gauss surface. So as a result, this particular Gauss surface is creating actually zero flux by itself. The electric field line that is coming is from the outside, external. Get the idea here what is going on?
Yes, sir.
সো দ্যাটস ইট। সো আমরা আজকে এখানে শেষ করছি, আমরা একটা অঙ্ক পরবর্তীতে করবো। আমি অবশ্য অঙ্কগুলো আমরা লেকচার নোটই দেওয়া থাকবে, কারণ ওটা সলভ করা, ওগুলো সব প্রবলেম সলভ করা আছে, এগুলো সব সলভ করা আছে, আপনারা দেখবেন। তবে আমরা একটা অঙ্ক হয়তো নেক্সট ক্লাসে করে পরে আমরা লেকচার গাউস লটা শুরু করে দেবো অফিসিয়ালি। ওকে,